All right, so here's where we are. We're talking about kinematics. No, we're not. Kinetics. Okay, so back to kinetics. Um, so we were talking about the force types. And there are two types of forces. It's split up into, first is the weight. And second is contact forces. And the contact forces are pushing forces. So pushing forces point toward the chosen object. Pulling forces, those act away from the chosen object. And now we're done talking about both of those, and we're going on to the last one, which is friction. And friction is resistance to sliding. And friction you can break up into two separate types, but we're only going to do one of these two. So one type of friction is called static friction. And that's the friction that keeps an object from starting to move. So it keeps, let me say it keeps an object at rest from starting to slide. Okay, so I'll do a demonstration. Just give me like 3 minutes to hobble over to this table. Okay, so here's static friction. So what forces are acting on the table right now without me touching it? Yeah, weight force and a pushing force from the ground. Okay, and nothing's happening horizontally, right? So it's no surprise that if you think about only the horizontal forces, it's no surprise that it would be a surprise if it started accelerating, right? But now, okay, so right now there are no horizontal forces. So Newton's second law, the x component in Newton's second law, just says 0 for the net force horizontally is equal to mass times 0 for the acceleration. But now I'm putting a, not very big, but I'm putting some horizontal force on it, okay? But it's still not accelerating. So what's going on there? Because Newton's second law says, so now I'm applying a horizontal force this way to it, okay? So F net is me pushing this way. There's still no acceleration, so there must be another force that's counteracting the force I'm applying to it, right? There has to be. Otherwise, as soon as I started pushing it, it would start accelerating. And that force that's counteracting it is the static friction force, and it's pushing exactly the opposite direction with exactly the same magnitude of force that I'm applying to it. And if I put a little bigger force into it, it applies a little bit bigger force back to keep it from accelerating. Okay, so that's static friction. And then kinetic friction is once it starts to slide, So this is going to make a horrible noise, but just imagine me sliding. So if it's sliding, imagine I'm sliding it now with a constant velocity. Okay, that's pretty close to a constant velocity. Okay, so I was putting a horizontal force into it this way. If that was the only horizontal force, what would you expect the table to do? Not just keep going. If I keep applying that force, it needs to accelerate. That's what Newton's second law says. So in other words, if I keep pushing on it with, it needs to be speeding up, okay? But it's not, it's moving with a constant velocity, even though I keep putting a force into it. Which means, again, the acceleration is 0. If the velocity is constant, the acceleration is 0. And so again, there has to be a force counteracting the force I'm putting into it. Okay, and that's the kinetic friction force. Okay, so one type is static friction, one type is kinetic friction. And this is a friction force that acts when an object is sliding. Okay, we could do both of these, but we're not going to, just in the interest of time. So I'm going to leave this off. And so the calculations we're going to do just involve kinetic friction, objects that are sliding. Calculations aren't really that different, but I'm going to skip this one. Okay, so what do we know about the kinetic friction force? Well, no matter how fast the object is sliding, or whether it's accelerating or not accelerating, the friction force vector is the same. Its direction is opposite the direction of motion. In other words, the opposite direction of the velocity vector. And its magnitude is this constant mu, the Greek letter mu, times the normal force. Where this Greek letter mu is called the coefficient of kinetic friction. And the units for that, it's just a number. It's a pure number. So it doesn't have any units attached. Okay, so that has no units. Of all the Greek letters, this is the easiest one to remember because mu is spelled mu, and it looks like an exact blend of a m and a u. So you never have to forget that one. The other ones are hard to remember, but that one's easy. Okay, so let's think about what these mean for a little bit, and then we'll start doing some example problems. Give me a couple minutes. Okay, so first of all, the direction is opposite the direction of motion. And in all of the Newton's second law problems we've done so far, we haven't cared about the direction of the velocity. A couple people in class even asked about that, like, which way is it moving right now? Is it rolling up or rolling down the incline? And the answer is, up until now, it hasn't mattered. the answer would be true whether it was rolling down at that instant or rolling up at that instant or at rest at that instant. But now it is going to matter, because if we do a problem for something like this, when it's sliding that way, which way does the kinetic friction force act? Yeah. And if I go to the other side and push it the other way, then the kinetic friction force does the exact opposite thing. Okay. And so now in every problem, that's why in every problem I give, I'm going to have an arrow showing the direction of motion in that instant. Because you need to know the direction of motion in order to know the direction of the friction force. The other thing, so that's the direction. And then looking at the magnitude, what that says is, so the coefficient of kinetic friction, that's something you can look up for two different materials. Like you could look up the coefficient of kinetic friction for like wood and steel or something, and it would give you the constant for two smooth, a smooth piece of steel sliding against a smooth piece of wood. But the fact that it's multiplied by the normal force means, and I think this is sort of intuitive, that the harder the two objects are mashed together, the more that friction force resists sliding. Okay, and so here's what that means. That means that it's pretty easy for me to get this sliding, but if I put 1,000 pounds of weights on top of it, it would be a lot harder for me to get it sliding. Okay, so that's what that says, and it sort of makes sense. All right, so let's start with some simple examples, and we'll just sort of work our way up. So first, I'll start out with a horizontal surface. And there's a box with a mass of 10 kilograms. And at this instant, it's sliding this way. So you can think of that as the direction of the velocity vector, or, that's the direction of motion. And let's say that there's a 30 Newton force applied this way. Okay, so in these, we always want to use like last time I talked about the coordinate system we're going to use for rolling and sliding problems. We're always going to choose a coordinate system where the positive y-axis points right out of the surface. We always want to do that with friction problems. And so the coordinate system, in this case, is going to be our usual one. There's the x-axis, there's the y-axis. And so here's a free body diagram. Okay, there's a weight force acting down. That's 10 times 9.81, so 98.1 newtons. And over here, there's this force acts on the surface, the 30 Newton force acts on the boundary. And then when you get down to the ground, there's still a normal force. The ground still keeps that from sinking into the ground. So there's a normal force like that. I forgot to get the coefficient of friction. And I forgot to say what we're calculating. Okay, so the coefficient of friction is, let's say it's 0.2. And we want to calculate the acceleration. There could be problems where you're given other stuff and you have to calculate the coefficient of friction, but most of the time, maybe all the time, you'll be given the coefficient. Okay, so we want the acceleration vector. And so the one thing we're missing is the friction force. Which way does the friction force act? It acts to the right. That's correct. And what's the magnitude? 0.2 times this n, because that n is a measure of how hard that box is being mashed against the ground. So I'm just going to write this as 0.2 n. And by the way, I think I mentioned this maybe before, but we have a capital N for newtons and a capital N for normal force. I always, when I mean normal force, I always put the fancy little hat and shoes on it. And when I mean newtons, I just leave it plain. So that's how you can tell what I'm talking about. Okay, so now go to Newton's second law. And in this coordinate system, that 30 Newton force is in the positive x direction. The weight force is in the negative y direction. The normal force is in the positive y direction. The friction force is in the positive x direction. And all that is equal to the mass of the body times the acceleration. And just like every other rolling or sliding problem, if you use that coordinate system rule that I brought up last time, we're going to treat the acceleration as just a0. Okay, so what we're trying to find is this vector. And to find that vector, all we need is the value for a. So usually, like up until now, we would just skip the y equation and just use the x equation to find a. But now we can't do that because there are two variables in the x equation, n and a. And so now this, you're going to have to do this order of steps in every one of these friction problems. We're going to use the y equation to solve for n, and then plug that value of n in there to solve for a. Okay, so the y equation says 0 minus 98.1 plus n plus 0 is equal to 0. And if you use that to solve for n, you get n is equal to 98.1. And that's in newtons. That might make you wonder if the normal force is always just equal to the weight of the object. Often it is, but not always. So you always want to do that calculation. Okay. And now we're going to plug that into the x equation. And the x equation says 30 plus 0 plus 0 plus 0.2 times 98.1 is equal to 10a. And so that says 49.62 is equal to 10a. And so a is equal to 4.962 meters per second squared. And now you can plug that value for a into the acceleration vector, and you get that the acceleration vector is equal to 4.9620. Or in other words, that's in the positive x direction. So the acceleration is this way at 4.962 meters per second squared. Any questions about that? Okay, well, in problems before, we haven't been able to say from our calculations whether an object is speeding up or slowing down because, like I said, our answer worked whether the velocity was this way or that way or it was at rest. Now our answers are always dependent on saying what direction the velocity is at that instant. So is this object speeding up or slowing down? Slowing down because the velocity is to the right. We calculated that the acceleration was, the velocity is to the left. Sorry, I was turned around. Velocity is to the left. We got the acceleration is to the right. And so they're in opposite directions, so it's slowing down. Okay. Before we started that, there was no way to know. Well, yeah, there is in that one. You won't always be able to tell by looking at it whether it's going to be speeding up or slowing down. In this case, you could because the only two forces are both going in the opposite direction of the velocity, but that won't always be the case. Well, if I would have applied a force of 30 newtons that way, it would have still been speeding up because the friction would be going this way, but it would have been overcome by the 30 newton force that way. Any other questions right now? It's always in the opposite of the motion. Right. What matters is the velocity vector. Yep. Yeah, I mean, I could write it either way. The velocity, I could have written this is the direction of the velocity, or I could have said this is the direction of motion. They mean the same thing. Yep. Yeah, if I give the direction of motion, that is giving you the direction of the velocity. Okay, let's do another one. Let's do one that's similar. Okay, so again, let's say we have a 10 kilogram box, a 30 Newton force. And again, let's say that it's moving to the left. And these are going to be the same. We'll keep the same coefficient of friction, and we'll still calculate the acceleration. But the difference here is now we'll say, let's apply 100 Newton force straight down. That could be something sitting on top of the box or something mechanically pushing down on it. What do you expect the answer to, how do you expect the answer to change on this one? Yeah, well, so it gets a little confusing, but what do you expect the friction force to be bigger or smaller? Friction force is going to be bigger. And now this thing is already slowing down. So bigger friction force is going to make it slow down more. Okay. And so this is actually going to have a bigger acceleration because that friction force is well, because the whole thing is slowing down already. Okay, so we have a weight force of 98.1, a force of 30 newtons to the right, and a force of 100 newtons down, and then a normal force up, and a friction force this way. And that friction force still is just equal to 0.2 times the normal. And so Newton's second law says 30, 0 plus 0, negative 98.1 plus 0, negative 100 plus 0n. Oh no. Okay, got most of it back anyways. Okay, we didn't lose much. Free body diagram. So a downward force of 98.1. You already have this all in your notes, so I'm just going to write it. Okay, and then Newton's second law says 30, 0 plus 0, negative 98.1 plus 0, negative 100 plus 0, n plus 0.2 n 0 is equal to the mass times the acceleration vector. And so just like we did last time, I'm first going to use the y equation to calculate n. And then I'm going to plug my value for n into the x equation to calculate the acceleration. And our goal is to come up with this vector, which requires figuring out that variable a. So the x equation says, nope, y equation is what we do first. So the y equation says 0 minus 98.1 minus 100 plus n plus 0 is equal to 0. And so this time n is equal to 198.1. So that normal force is bigger because that 100 Newton force is mashing those two surfaces together. And then the x equation says 30 plus 0 plus 0 plus 0 plus 0.2 times 198.1 is equal to 10a. And so 30 plus is that 39.62 is equal to 10a. And so 69.62 is equal to 10a. And so a is equal to 6.962 meters per second squared. And now that we have a, if we plug that back into the acceleration vector, the red dotted line, we get that the acceleration vector is 6.962 or a magnitude of 6.962 in the positive x direction. So this way. Okay, so is the box speeding up or slowing down? Slowing down because that's opposite the velocity. Is it slowing down more or less than it was in the first example? More, because we have more friction counteracting the motion. So if you increase the friction in the same problem, it either makes it slow down faster, or if in the first case, the lower friction case, it was speeding up, it would make it speed up less. Those are the two options. Speed up less or slow down more. Okay, so now I'm going to do one on an incline. So let's say we have an incline of 30 degrees. And a 10 kilogram box sliding down the incline at this instant. So that's the direction of motion. And let's say that for these two materials, the coefficient of friction is 0.10. And we want to calculate the acceleration vector. And there are no other forces acting on it except the contact and the weight. Okay, so what do we want the coordinate system to look like? It has to be at an angle. The y-axis is pointing straight out of the surface. So it has to look like this. And then a free body diagram. There's a weight force acting down. So that's 10 times 9.81 is 98.1 again. And then go around the boundary. The only place that there's contact between the surroundings and the boundary is where it's in contact with the ground. And that is made up of a normal force and a friction force. Which way does the friction force act? The right, yep. It has to be opposite the direction of motion. And that's equal to 0.1 n. This time the coefficient is 0.1. And then Newton's second law. Okay, well, actually, let me set that aside for a minute. So let's first figure out, so remember that the one drawback of using the rotated coordinate system is that we have to figure out the components of the weight force. So let's do that first. So our coordinate system is like this. Our weight force is straight down. So remember that any angle between the horizontal and the incline is the same as the angle between the weight force and the negative y-axis. So this has to be 30 degrees. The angle that we want for cosine and sine is from the positive x-axis to the weight force. So what's theta in this case? Yep, it falls 30 degrees short of making it to that 270 line. So theta is equal to 240 degrees. Anybody have any questions about that? Does that make sense? So then the vector, what? Yes, in our rotated coordinate system. Yep. And so that weight force vector is 98.1 times the cosine of 240, 98.1 times the sine of 240. Can someone calculate that for me? Okay. Okay. Yeah, that makes sense. Okay. So negative 49.05 and then negative 84.96. Okay. Okay. So now Newton's second law. So we have the weight force that we just calculated. We have the normal force, the friction force, and that's equal to the mass times the acceleration. And, you know, one of the nice things about using this rotated coordinate system is the acceleration always shows up the same way. So the y equation says negative 84.96 plus n plus 0 is equal to 0. So n is equal to positive 84.96. And then plug that into the x equation, and it says negative 49.05 plus 0 plus 0.1 times 84.96 is equal to 10a. So negative 49.05 plus 8 point, I'll write that as 50, is equal to 10a. And so that says negative 40.55, yes, is equal to 10a. And so a is equal to negative 4.0, I'll call it 6. And now plug that back into the acceleration vector, this thing. And you get that the acceleration vector is equal to negative 4.060. Or that's in the negative x direction, which is down the incline with a magnitude of 4.06. Okay, so in this case, is that box speeding up or slowing down? Speeding up. Does that make sense? Well, yeah, so basically, you know, gravity is trying to make it speed up. The friction force is always trying to slow it down. In this case, because the thing is too steep and the coefficient of friction is too little, gravity wins out and it speeds up. Okay. So think about this. If we kept increasing the coefficient of friction, if we kept increasing that value of mu, we could find a value of mu where the acceleration was exactly equal to 0. Okay? What would that mean? Well, it would still be moving. It just means the velocity would not be changing. So whatever velocity it had at that instant, it would keep sliding down the ramp at that velocity. Okay? And that coefficient would have to be something bigger than 0.1. Anybody want to do it? That's boring. Okay. Well, let me give you one to do. Okay, so let's say we have an incline of 10 degrees. And let's say this is gonna, okay. Let's say this has a mass of 5 kilograms and there's a force pushing it straight into the surface of 20 newtons. And let's say that at this instant, the object is moving up the ramp. Say the coefficient of friction is 0.2. And we want to know what's the acceleration and is it speeding up or slowing down? Okay, so first of all, let's just try to make sense out of this problem. So all we don't have anything at this instant pushing it up the ramp. We have a friction force that's actually being even increased a little bit by that 20 Newton force. So does it make sense that this box is sliding up the ramp at that instant? I mean, you would think not, kind of. There's nothing making it go up. But remember this, the velocity vector doesn't have to do with the forces that are acting at that instant. The only thing that has to do with the forces at that instant is the acceleration. The velocity is determined by all the forces that happen in that thing's past. Okay, so what could have happened here is that a big force, 200 newtons, for the last 5 seconds has been pushing this up the ramp, and then all of a sudden that force disappears and this force is applied. For a couple of seconds at least, I mean, this thing would be going really fast. So at least for a couple of seconds, even with those forces acting on it, it's going to keep sliding up the ramp. But if your intuition is that it's going to be slowing down because of the forces acting on it now, that's correct. Because the only forces you have are gravity trying to pull it down the ramp and a friction force trying to slow it down. This is totally possible, is what I mean. The velocity does not have to do with those forces that are drawn on there. Okay, so take a few minutes and work together and see if you can get through this. And after you've worked on it for a while, I'll go through it. And feel free to, like whenever I do this, what I would recommend you do, just compare what I'm doing to what you did. And it's a good way to bring out what the points are where you misunderstood something, like you find the spot where like, oh, I did this wrong, then that's something you can sort of focus on, Okay, so first, the coordinate system is going to be like this. So the x-axis is down the incline. A free body diagram. There's a weight force. That's 5 times 9.81, so 49.05. There's the 20 Newton force. There's a normal force up, or not up, I mean perpendicular to the surface. And then opposite the direction of motion is the coefficient times the normal force, so that's 0.2 times n. To figure out the components of the weight force, the weight is straight down like this. This angle is 10 degrees. Theta is this. So theta is equal to 270 plus 10, so 280. Coordinate system. There's a in your notes from last class, there's a list of like the benefits and the cost. It makes it harder to deal with the weight force, but everything else on here it makes easier to deal with. The normal force, you only have one component in normal force. Friction force, you have one component, acceleration. So it's sort of like a trade-off thing, but it comes out in our favor. But it is probably a good thing to remember that there's no reason you have to do this to get the right answer. The math would just be a lot more complicated if you kept the usual coordinate system. Okay, so weight force is 49.05 times the cosine of 280. 49.05 times the sine of 280. What do you get for those components? Okay. Thank you. Okay, so now Newton's second law. We have the weight force. Plus the normal force. Plus the 20 Newton force. Plus the friction force. Is equal to the mass times the acceleration. The y equation says negative 48.30 plus n minus 20 plus 0 is equal to 0. And so n is equal to 68.30 newtons. And then the x equation says 8.52 plus 0 plus 0 plus 0.2 times what we calculated for the normal force is equal to 5a. And so what do you get for a? So positive 4.436 meters per second squared. So the acceleration vector is 4.4360. Or is that 4.436 meters per second squared the ramp or down the ramp? down, yep. That's a terrible line. Okay, 4.436 meters per second squared. So is this box speeding up or slowing down? Slowing down, yep. Just like we sort of, just from intuition, knew it had to be. Anybody have any questions about that one? Okay, let's do the quiz. Just give me 2 minutes to get over there to hand them out.